a WikiVidi Documentaries production. Don't forget to like and subscribe. Enjoy. ʻOumuamua. ʻOumuamua is the first interstellar object detected passing through the solar system, formally designated 1I/2017 U1. It was discovered by Robert Weryk using the Pan-STARRS telescope at Haleakala Observatory, Hawaii, on the 19th of October 2017, 40 days after it passed its closest point to the Sun. When first seen, it was about from Earth, and already heading away from the Sun. ʻOumuamua is a small object, estimated to be about 230 in size. It has a dark red color, similar to objects in the outer solar system. ʻOumuamua showed no signs of a comet tail despite its close approach to the Sun, but has since undergone non-gravitational acceleration, potentially consistent with a push from solar radiation pressure. It has significant elongation and rotation rate, so it is thought to be metal-rich with a relatively high density. ʻOumuamua is tumbling, rather than smoothly rotating, and is moving so fast relative to the Sun that there is no chance it originated in the solar system. It also means that ʻOumuamua cannot be captured into a solar orbit, so it will eventually leave the solar system and resume traveling through interstellar space. ʻOumuamua's system of origin and the amount of time it has spent traveling amongst the stars are unknown. Nomenclature. As the first known object of its type, ʻOumuamua presented a unique case for the International Astronomical Union, which assigns designations for astronomical objects. Originally classified as Comet C/2017 U1, it was later reclassified as Asteroid A/2017 U1, due to the absence of a coma. Once it was unambiguously identified as coming from outside the solar system, a new designation was created, I, for interstellar object. ʻOumuamua, as the first object so identified, was designated 1I, with rules on the eligibility of objects for I numbers, and the names to be assigned to these interstellar objects, yet to be codified. The object may be referred to as 1I, 1I/2017 U1, 1I/ʻOumuamua, or 1I/2017 U1. The name comes and reflects the way this object is like a scout or messenger sent from the distant past to reach out to humanity. It roughly translates to first distant messenger. The first character is a Hawaiian okina, not an apostrophe, and is represented by a single quotation mark and pronounced as a glottal stop. The name was chosen by the Pan-STARRS team in consultation with Kai Yukimura and Larry Kimura of the University of Hawaii at Hilo. Before the official name was decided upon, the name Rama was suggested. The name given to an alien spacecraft discovered under similar circumstances in the 1973 science fiction novel Rendezvous with Rama by Arthur C. Clarke. Observations and conclusions concerning the trajectory of ʻOumuamua were primarily obtained with data from the Pan-STARRS 1 telescope, part of the SpaceGuard survey, and the Canada-France-Hawaii telescope, and its composition and shape from the Very Large Telescope and the Gemini South Telescope in Chile, as well as the Keck 2 telescope in Hawaii. These were collected by Karen J. Meach, Robert Weryk and their colleagues, and published in Nature on 20th of November, 2017. Post-announcement, the space-based telescopes Hubble and Spitzer joined in the observations. ʻOumuamua is small and dark. It was not seen in stereo high 1A observations near its perihelion on the 9th of September 2017, limiting its brightness to 13.5 mag. By the end of October, ʻOumuamua had already faded to apparent magnitude 23. And by mid-December 2017, it was expected to be too faint and fast-moving to be studied by even the largest ground-based telescopes. ʻOumuamua was compared to the fictional alien spacecraft Rama, because of its interstellar origin. Adding to the coincidence, both the real and the fictional objects are unusually elongated and limited in size. However, ʻOumuamua has a reddish hue and unsteady brightness, which are typical of asteroids. The SETI Institute's radio telescope, the Allen Telescope Array, examined ʻOumuamua, but detected no unusual radio emissions. More detailed observations, using the Breakthrough Listen hardware and the Green Bank telescope, were performed. The data were searched for narrowband signals and none were found. Given the close proximity to this interstellar object, limits were placed to putative transmitters with the extremely low power of 0.08 watts. Trajectory. ʻOumuamua appears to have come from roughly the direction of Vega in the constellation Lyra. The incoming direction of motion of ʻOumuamua is 6 degrees from the solar apex, which is the most likely direction for approaches from objects outside the solar system. On the 26th of October, 2 recovery observations from the Catalina Sky Survey were found dated 14 and the 17th of October. A 2-week observation arc had verified a strongly hyperbolic trajectory. It has a hyperbolic excess velocity of its speed relative to the Sun when in interstellar space. By mid-November, astronomers were certain that it was an interstellar object. Based on observations spanning 34 days, Oumuamua's orbital eccentricity is 1.20, the highest ever observed. An eccentricity exceeding 1.0 means an object exceeds the Sun's escape velocity, is not bound to the solar system and may escape to interstellar space. While an eccentricity slightly above 1.0 can be obtained by encounters with planets, as happened with the previous record holder, C/1980E1. Oumuamua's eccentricity is so high that it could not have been obtained through an encounter with any of the planets in the solar system. Even undiscovered planets, if any exist, could not account for Oumuamua's trajectory. Any undiscovered planet must be far from the Sun and hence moving slowly according to Kepler's laws of planetary motion. Encounters with such a planet could not boost Oumuamua's speed to the observed value, and therefore Oumuamua can only be of interstellar origin. Oumuamua entered the solar system from north of the plane of the ecliptic. The pull of the Sun's gravity caused it to speed up until it reached its maximum speed as it passed south of the ecliptic on the 6th of September, and made a sharp turn upward at its closest approach to the Sun on the 9th of September at a distance of from the Sun, i.e. about 17% closer than Mercury's closest approach to the Sun. The object is now heading away from the Sun towards Pegasus at an angle of 66 degrees from the direction of its approach. On the outward leg of its journey through the solar system, Oumuamua passed within the orbit of Earth on the 14th of October at a distance of approximately from Earth, and went back north of the ecliptic on the 16th of October and passed beyond the orbit of Mars on the 1st of November. It passed beyond Jupiter's orbit in May 2018, and will pass beyond Saturn's orbit in January 2019 and Neptune's orbit in 2022. As it leaves the solar system, it will be approximately right ascension 23 hours 51 minutes and declination 24 degrees and 45 minutes in Pegasus. It will continue to slow down until it reaches a speed of 26.33 kilometers per second relative to the Sun, the same speed it had before its approach to the solar system. It will take the object roughly 20,000 years to leave the solar system completely. On the 27th of June 2018, astronomers reported a non-gravitational acceleration to Oumuamua's trajectory, potentially consistent with a push from solar radiation pressure. Initial speculation as to the cause of this acceleration pointed to comet off-gassing, whereby portions of the object are ejected as the Sun heats the surface. However, multiple objections have been raised to this possibility. Researchers point out that no such tail of gases was ever observed following the object. Additionally, the anomalous acceleration was not observed when Oumuamua was passing at its closest to the Sun as would be expected. A follow-up analysis of these claims identifies that, were Oumuamua a comet, the off-gassing should have caused such an increase in rotational torque as to tear the object apart. Indications of origin. Accounting for Vega's proper motion, it would have taken Oumuamua 600,000 years to reach the solar system from Vega. But as a nearby star, Vega was not in the same part of the sky at that time. Astronomers calculate that 100 years ago the asteroid was 561 ± from the Sun and traveling at 26.33 kilometers per second with respect to the Sun. This interstellar speed is very close to the mean motion of material in the Milky Way in the neighborhood of the Sun, also known as the local standard of rest, and especially close to the mean motion of a relatively close group of red dwarfs. This velocity profile also indicates an extrasolar origin, but appears to rule out the closest dozen stars. In fact, The strong correlation between Oumuamua's velocity and the local standard of rest might mean that it has circulated the Milky Way several times and thus may have originated from an entirely different part of the galaxy. It is unknown how long the object has been traveling among the stars. The Solar System is likely the first star system that Oumuamua has closely encountered since being ejected from its birth star system, potentially several billion years ago. It has been speculated that the object may have been ejected from a stellar system in one of the local kinematic associations of young stars within a range of about 100 parsecs, some 45 million years ago. The Carina and Colombo associations are now very far in the sky from the Lyra constellation, the direction from which Oumuamua came when it entered the Solar System. Others have speculated that it was ejected from a white dwarf system and that its volatiles were lost when its star became a red giant. About 1.3 million years ago the object may have passed within a distance of 0.16 pc to the nearby star Tyche 4742, 10271, but its velocity is too high to have originated from that star system, and it probably just passed through the system's Oort cloud at a speed of. A more recent study using Gaia data released 2 has updated the possible past close encounters and has identified 4 stars that Oumuamua passed relatively close to and at moderately low velocities in the past few million years. This study also identifies future close encounters of Oumuamua on its outgoing trajectory from the Sun. According to one hypothesis, Oumuamua could be a fragment from a tidally disrupted planet. This makes Oumuamua a rare object, much less abundant than other extrasolar, dusty snowball, comets or asteroids could be. Classification. Initially, Oumuamua was announced as Comet C/2017 U1 based on a strongly hyperbolic trajectory. In an attempt to confirm any cometary activity, very deep stacked images were taken at the Very Large Telescope later the same day, but the object showed no presence of a coma. Accordingly, the object was renamed A/2017 U1. Becoming the first comet ever to be redesignated as an asteroid. Once it was identified as an interstellar object, it was designated 1I/2017 U1, the first member of a new class of objects. The lack of a coma limits the amount of surface ice to a few square meters, and any volatiles must lie below a crust at least thick. It also indicates that the object must have formed within the frost line of its parent stellar system or have been in the inner region of that stellar system long enough for all near-surface ice to sublimate, as may be the case with Damocloids. It is difficult to say which scenario is more likely due to the chaotic nature of small body dynamics, although if it formed in a similar manner to solar system objects, its spectrum indicates that the latter scenario is true. Any meteoric activity from Oumuamua would have been expected to occur on the 18th of October 2017 coming from the constellation Sextans. But no activity was detected by the Canadian Meteor Orbit Radar. On the 27th of June 2018, astronomers reported that Oumuamua was thought to be a mildly active comet, and not an asteroid, as previously thought. This was determined by measuring a non-gravitational boost to Oumuamua's acceleration, consistent with comet outgassing. However, studies submitted in October 2018 suggest that the object is neither an asteroid nor a comet. Appearance, shape, and composition. Spectra recorded by the William Herschel telescope on the 25th of October showed that the object was featureless and colored red like Kuiper belt objects. Spectra from the Hale telescope showed a less red color resembling comet nuclei or trojans. Its spectrum is similar to that of D-type asteroids. Oumuamua is rotating around a non-principal axis, a type of movement known as tumbling. This accounts for the various rotation periods reported, such as 8.10 hours, with a light curve amplitude of, whereas Meech et al. Reported a rotation period of 7.3 hours, and a light curve amplitude of 2.5 magnitudes. Most likely, Oumuamua was set tumbling by a collision in its system of origin, and remains tumbling since the time scale for dissipation of this motion is very long, at least a billion years. The large variations on the light curves indicate that Oumuamua may be either a highly elongated object, comparable to or greater than the most elongated solar system objects, or an extremely flat object, a pancake or oblate spheroid. However, The size and shape have not been directly observed, as ʻOumuamua appears as nothing more than a point source of light even in the most powerful telescopes. Neither the albedo or triaxial ellipsoid shape are precisely known. If cigar-shaped, the longest to shortest axis ratio could be 5:1 or greater. Assuming an albedo of 10% and a 6:1 ratio, ʻOumuamua has dimensions of approximately 230 with an average diameter of about. According to astronomer David Jewett, the object is physically unremarkable except for its highly elongated shape. Bannister et al. Have suggested that it could also be a contact binary, although this may not be compatible with its rapid rotation. One speculation regarding its shape is that it is a result of a violent event that caused its ejection from its system of origin. JPL News reported that ʻOumuamua is up to 1/4 mile, 400 meters, long, and highly elongated, perhaps 10 times as long as it is wide. Light curve observations suggest the asteroid may be composed of dense metal-rich rock that has been reddened by millions of years of exposure to cosmic rays. It is thought that its surface contains tholins, which are irradiated organic compounds that are more common in objects in the outer solar system and can help determine the age of the surface. This possibility is inferred from spectroscopic characterization and its dark and reddened color, and from the expected effects of interstellar radiation. Despite the lack of any cometary coma when it approached the Sun, it may still contain internal ice, hidden by an insulating mantle produced by long-term cosmic ray exposure. Additional measurements. In December 2017, astronomer Avi Loeb of Harvard University, an advisor to the Breakthrough Listen project, cited ʻOumuamua's unusually elongated shape as one of the reasons why the Green Bank telescope in West Virginia would listen for radio emissions from it to see if there were any unexpected signs that it might be of artificial origin, although earlier limited observations by other radio telescopes such as the SETI Institute's Allen Telescope Array had produced no such results. On the 13th of December 2017, the Green Bank telescope observed the asteroid for 6 hours across 4 bands of radio frequency. No radio signals from ʻOumuamua were detected in this very limited scanning range, but observations are ongoing. In September 2018, astronomers described several possible home star systems from which ʻOumuamua may have begun its interstellar journey. In November 2018, Shemuel Bialy and Abraham Loeb, astronomers from Harvard University, submitted a paper exploring the possibility of ʻOumuamua being an artificial thin solar sail accelerated by solar radiation pressure in an effort to help explain the object's non-gravitational acceleration. Other scientists have stated that the available evidence is insufficient to consider such premise. Hypothetical space missions. ʻOumuamua was at first thought to be traveling too fast for any existing spacecraft to reach. The Initiative for Interstellar Studies launched Project Lyra to assess the feasibility of a mission to ʻOumuamua. Several options for sending a spacecraft to ʻOumuamua within a time frame of 5 to 10 years were suggested. One option is using first a Jupiter flyby followed by a close solar flyby at 3 solar radius in order to take advantage of the orbit effect. Different mission durations and their velocity requirements were explored with respect to the launch date, assuming direct impulsive transfer to the intercept trajectory. Using a powered Jupiter flyby, a solar orbit maneuver, and Parker Solar Probe heat shield technology, a Falcon Heavy class launcher would be able to launch a spacecraft of dozens of kilograms towards 1I/ʻOumuamua, if launched in 2021. More advanced options of using solar, laser electric, and laser sail propulsion, based on breakthrough starshot technology, have also been considered. The challenge is to get to the asteroid in a reasonable amount of time, and yet be able to gain useful scientific information. To do this, decelerating the spacecraft at ʻOumuamua would be highly desirable, due to the minimal science return from a hypervelocity encounter. If the investigative craft goes too fast, it would not be able to get into orbit or land on the asteroid and would fly past it. The authors conclude that, although challenging, an encounter mission would be feasible using near-term technology. Seligman and Laughlin adopt a complementary approach to the Lyra study, but also conclude that such missions, though challenging to mount, are both feasible. and scientifically attractive. Brought to you by WikiVidi Documentaries. Would you like to know more?